Hello again. This is video lecture 24.5, and we're going to be studying the electric potential of a charged, isolated conductor. So we're back to that situation that we've talked about before, about a conductor in electrostatic equilibrium. Electrostatic equilibrium. I'm abbreviating it there so I can fit it on the screen, which we have talked about before, and I'm going to review some of the properties of a conductor in electrostatic equilibrium, and I'm going to add one more new one that we became familiar with in the most recent, in the previous experiment that we did. So, properties of an isolated conductor in electrostatic equilibrium. All very important things to remember. Now remember, it's a conductor, and the hallmark of a conductor is that inside it has to have basically an unlimited number of free charges, charges that can move freely about the body of the conductor. Usually those are just plain old electrons. So given that we have such a conductor and it's in electrostatic equilibrium, here are the properties it must have. The electric field equals 0 in the body of the conductor. That is the most important one to remember. Okay? I'm going to jump down and do this one next. If the conductor has a net charge, it might not, but if it does, then that charge must reside all on the conductor's surface. Must be on the surface of the conductor. All right, now, if we are at a surface of a conductor that has charge, then if you're at a point just above that surface, I mean just above, then there's going to be an electric field up there, because you're not in the body of the conductor, and that electric field must be perpendicular to the surface. It can have no component along the surface, and the magnitude of that electric field just above the surface is sigma over epsilon 0. We really ought to write it as the absolute value of sigma over epsilon 0, where sigma is the surface charge density at the location where you are. And it doesn't have to be the case that sigma is uniform over the conductor's surface. It depends upon the conductor's shape and if there are any other charges around. Okay, now those are actually all ones we've done before. You might not have remembered all of them. I want you to, but we've talked about those before. Chapter 23. Now in this chapter 24, we're adding one more new one that's also very important. And it involves the concept of electric potential, which is the topic of chapter 24. And here's the new property of a conductor in electrostatic equilibrium. Every point on the surface and in the interior body of an isolated conductor will be at the same potential in volts. That means every point on the surface and in the body of the isolated conductor is one big equipotential, because every point is at the same potential in volts. And we've got a little drawing down here below of something that's supposed to make you think of some sample of conductor, like a piece of gold. And we've picked 2 points inside the body of the conductor. We've labeled them I and F. And I've even sketched a jagged path to travel from I to F. And I want to show you now where this new property comes from. Okay? It comes from this, one of the most important formulas in chapter 24, that enables us to calculate the potential difference between 2 points by doing a line integral of the electric field between those points. And that's what I'm going to apply here, because I want to calculate the potential difference between the final point that I picked in the body of the conductor and the initial point by doing the integral of the negative integral of E dot ds. But remember, at every point in the body of the conductor, E equals 0. Very first property. So my integral E dot ds means just integrate 0 dot ds. Just add up a bunch of zeros. You have to get 0 for that integral. But then that integral equals V final minus V initial. So it must be that V final equals V initial. And this point have the same potential. But those points were arbitrarily chosen inside the body. So every point inside the body, including right on the surface, must be at the same potential. Okay? The conductor in electrostatic equilibrium is one big equipotential. Now here's something we like to do to make it look a little bit more challenging, but it's not just to give you a challenge, it's because the next thing I'm about to talk about is taking you a step closer to what physicists really deal with in the lab when they're doing experiments. And that is, you take your conductor and you hollow out some interior region, make it and have it empty. So let me shade in the part where the conductor is. That's the conductor, the isolated conductor in electrostatic equilibrium. And then this inner region here, hollow and empty. Okay? I'm assuming that nobody put an isolated charged particle in that hollow region. It's empty. Okay? Then an interesting question arises. What if I pick a point, I'm going to erase that word I just write in there. What if I pick a point I that's somewhere in that hollow part and a point F that's in the body of the conductor? Are those 2 points at the same potential, even though I isn't in the body of the conductor? Well, let's just pick a path. I'll just go a straight line between I and F, and let's use this integral over here and see what we get. Now we know that when we're on the part of the curve, or on the path that's in the body of the conductor, right along there, the electric field is definitely 0. So the integral of E dot ds along that part is 0. What about along this part of the path, starting at I, going into the hollow region until I get to the conductor? Well, I contend the electric field has to be 0 there too, because if it's a hollow region and there aren't any charged particles in there, there can't be any E. So you're still going to have the integral of 0 dot ds along that path, and therefore V final minus V initial equals 0, so V final and V initial are equal. So even points in that hollow interior are at the same potential as the points in the body of the conductor. Now it's different if somebody puts a charged particle in the hollow part, okay? I'm assuming that the hollow region is empty or not charged. There could be something in there, but it has no charge. So let's go straight to practicing with that concept. Here's an isolated spherical conductor. In fact, what it is an isolated spherical conducting shell. We love those kinds of shapes, don't we? So here we have an isolated spherical conducting shell. It's got a radius big R, and it's got a total charge big Q. It's charged. Notice the interior region is empty, hollow and empty. So that charge big Q, let's assume it's positive for now, would be spread out over the outside surface. And then you can have electric field lines radiating outward, uniformly and radially in all directions, like that. Okay? And the interior part is empty. Okay, so here's what we want to talk about in part A. Using a reference point out at infinity, where by definition the electric potential will equal 0, we are to sketch the electric potential V as a function of what's called little r, where little r is just the radial distance from the very center point there, out to wherever you are. Out to there, or there, or there, or there, or there, however far out. Okay? We're going to sketch the electric potential as a function of r, and we will assume that the big Q is positive. Let me draw that sketch down here. Well, the first thing I'm going to consider is outside the shell. Notice that would mean that. Little r is greater than big R. If you're outside the shell, probably the easiest thing to do is just use the shell theorem and collapse the shell to a point with all the charge big Q at the very center, and the electric potential for a point particle is easy to write down. It's the charge of the particle over 4 pi epsilon 0 times the distance you are from it. Well, if the particle's at the center, then your distance is just little r. Note, if I go to the limit as little r goes to infinity, I'm infinitely far away, that potential is 0. Okay? And in fact, you can use that for r greater than or equal to big R. And so right at the surface of the conductor, V at big R, of course, what you would have is Q over 4 pi epsilon 0 big R. Because when you're on the surface of this conductor, and you can assume it's wafer thin, this conductor, this conducting shell, then you're at a distance where little r equals big R. Okay? But now remember, once you are on the surface of the conductor and inward, even in the hollow region inside, everything must be an equal potential. Okay? And so the potential must have the same value everywhere for little r less than or equal to big R. Because from there on in, you're starting on the surface of the conductor and you're going in, and it must all be an equal potential. So with that in mind, let me make a sketch of the electric potential, V, as a function of R, versus little r, where that goes from 0 to big R, and then on outward. All right, so let's put a tick point on the v-axis and label that Q over 4 pi epsilon 0 big R. And then I know that the potential is constant at that value everywhere inside the conductor up to the surface. Then it drops off like 1 over the distance, Q over 4 pi epsilon 0 little r. It just asymptotically approaches 0, like that. Okay? So when you're outside, the shell looks like a particle. You've got Q over 4 pi epsilon 0 little r. And once you hit the surface of the shell and go inward, you're constant at Q over 4 pi epsilon 0 big R. Notice then that inside the shell, the potential is not 0, but the electric field is 0. Because the electric field is coming from the rate of change of the potential. And if the potential is constant in a region, then there is no electric field. Now, part B of this little practice asks us to make a similar sketch for the case where this sphere had negative charge. So then what I'm saying is that the charge on the outside surface is negative. So these would all be negative charge amounts. You see what would be different? The field lines would now point radially in towards the surface, not radially out. And what would the plot look like? Well, let me give myself some room here because I'm just going to add it to this plot for part B. Well, I would still have a formula like this for points outside the shell, but now that big Q is negative, right? So it would really, I would just write it like that. Okay? And then again, negative. So it just looks like this one over here, except it's on the negative side. Negative big Q over 4 pi epsilon 0 big R. And then we're constant at that value up to the surface, and then we just asymptotically approach 0. But that's what it would look like, the potential, if we had a negatively charged shell. All right, now I want to just show you some pictures to close out this video, and then we're going to talk about this content in our Friday class. So here's a picture that shows a lot that's been going on, but it's a conductor that's in an external electric field. It's not connected, this conductor, to anything, so in that sense it's isolated. but it's still immersed in an external electric field. And so what we had here is initially we had a uniform external electric field pointing to the right. And that's kind of shown by the field lines here and here on the edges, because they're uniformly spaced and they point to the right. But then we immersed into that this rather oddly shaped conductor, isolated, not connected to anything. So in the body of that conductor, the electric field must equal 0. So there can't be any electric field lines piercing inside that body of that conductor. Yet there's this external field. So why don't you have just electric field lines going straight through? Like that. Okay? Well, basically the conductor itself won't allow that to happen. Because what will happen is you'll get positive and negative charge induced over some regions of the surface. You'll get more negative charge induced on the left side, leaving you more positive charge induced on the right side. And those charges will distribute themselves just right on that surface, okay, on that surface, such that the electric field produced by the induced surface charge on the conductor plus the uniform external electric field to the right will give me a net electric field that is 0 in the body of the conductor and has the shape you see with the blue lines outside the conductor. Notice the blue lines, some of them have curvature, and some of them come into and terminate on the surface of the conductor, but they do so at a right angle. And some come out of the conductor and go onward, again at a right angle. But the amazing thing is that the conductor will induce surface charge that will produce its own electric field, such that the surface charge's electric field plus the original or uniform electric field will result in no field inside the conductor. It's really quite amazing. Let me show you a simpler shape where it might be a little bit easier to see how that happens. So on the left we have a uniform external electric field pointing to the right, and that's what those little arrows pointing to the right are in the XY plane. Now the circle there shows where we're going to put a spherical conductor, but it's not there yet. So right now we have a uniform electric field pointing to the right. Now the second picture over here on the right shows what happens when we immerse a spherical conductor into this external field. There will be charge induced on the surface of the conductor, okay, with negative charge induced on the left hemisphere of the sphere and positive charge induced on the right hemisphere of the sphere. And the picture I'm showing you on the right is the electric field due to just that induced surface charge on the surface of the conducting sphere. It's pretty complicated, isn't it? But there's one amazing thing about it. Look very carefully in the interior region of the spherical conductor. Now this is just due to the surface charge on its surface. It's uniform and it points to the left. I say again, it's uniform and it points to the left. The conductor will distribute that surface charge on its surface so that this happens. So that the interior field is uniform and points to the left. In fact, it's uniform and it points to the left, and it's exactly the same magnitude as the uniform field to the right that's in the left picture. So that when I add the uniform field to the right and the left picture and the uniform field to the left on the right side, they cancel in the body of the conductor. So when you combine these two pictures, you'll have the net electric field, and you will have no field in the body of the spherical conductor. E equals 0. It's really amazing. First of all, that the conductor can do that, and that somehow it figures out how to do it. Okay? And then what you have in this picture is the final electric field in the whole region, with the E equal to 0 in the body of the conductor, and this complicated electric field outside, with some of the electric field lines curving in and terminating on the surface or springing out from the surface. I even drew some equipotential contours that cross the electric field lines at right angles. This is basically the picture you were asked to draw in the electric field mapping experiment. Okay, this picture. And if you want to study this in more detail, take Physics 360, Electricity and Magnetism. We will actually solve this problem completely in Physics 360. Okay? But now I'm just showing you kind of what happens. And you end up with the conductor having zero field in the body of it, and a complicated electric field line structure outside, with some field lines coming in or out of the surface of the conductor, but doing so at a right angle to the surface. And in fact, that's where you get situations like this, which show a device called a Tesla coil, creating a very large electric field, causing the air to undergo what's called dielectric breakdown and become a conductor, and then the Tesla coil discharges to ground with that very big electric spark. But then you got a person inside a conductor, a car, okay, with tires that have some conducting material in them. And then in the body of the conductor, where the person is, the electric field is zero. So the person is safe from that spark. You can even see the path somewhat of that spark. It comes down, goes to the body of the conductor, and then there's a little there's a wire they've put to help it discharge to ground there, the spark. Person is safe because they're inside the hollow part of a conductor where the electric field must be zero. Okay? When you use a device, a conductor like this, it's called a Faraday cage. And the reason physicists find this important is because if you need to do an experiment where the equipment you're using is sensitive to electric charge and electric fields, and you don't want the equipment to be affected by electric fields, put it inside a hollow conductor. And then the experiment that you're going to do can be shielded from outside electric fields. And physicists do this all the time. They call it a Faraday cage. And you'll find even entire rooms that have a big steel mesh around the exterior of them, so that the interior of the room is shielded from external electric fields. Okay? All right, so conductors in electrostatic equilibrium, and we're going to talk more about those in our upcoming class. But that's all for this video.